Hi, we are 3 Sigma and you're in for a ride.
Have a safe flight. It's the last thing we hear before we go on a flight, and yet we seldom think about what goes into flying safely, because fatal accidents are few and far between. Nonetheless, providing passengers with consistently safe flights is a delicate balance between cost and safety regarding maintenance. It's important to note that the profit margins on most commercial airlines are razor thin, with the average being just 1.2% in the US, less than 1/10 of the national corporate average. As such, any unnecessary cost kneecaps the overall profitability of the airline. Keeping this in mind, it is in an airline's best financial interest to conduct maintenance as few times as possible while still holding high standards for safety.
Jet engines are a perfect example of where airlines must focus on hardware degradation. Jet engines provide the thrust required for liftoff and smooth flying in the skies. As such, a malfunction or failure of an engine, specifically mid-flight, can quickly become an obstructing issue. Typically, an engine failure will not result in the dreaded worst-case scenario, a crash. Instead, the aircraft will have to restructure its flight, possibly resulting in passengers being late or even missing connecting flights. So, after this sequence of events, the airline has lost money from physical damage caused to the jet engine, and the airline has lost money from the backlog in flight schedules due to the aircraft likely being taken out of service for engine repair. In addition, if an airline had delays caused by engine failure consistently, consumers may look to other airlines which sell the same flights to the same places at similar prices, but without the delays.
So, this begs the question, how can an airline minimize engine failures? It comes down to whether a company can find problems with engines efficiently and before the engine fails during flight, because with the high-speed movement and mechanical parts, the question is not if the part will fail, but when.
We should consider 3 different types of maintenance for jet engines. The first is preventative maintenance, which consists of checking a machine regularly for issues and deterioration. If there appears to be any, the machine undergoes the maintenance process. Next is run-to-failure maintenance, which does not rely on a schedule. Instead, when the machine fails, only then will a maintenance and repair be conducted. This type of maintenance may be applicable for non-critical components, for which regular maintenance would be cost ineffective. Lastly, there's predictive maintenance, which utilizes a machine learning model to estimate when a machine will fail, and, if possible, in which way. In addition, using predictive models, machines are monitored before they fail, with the deteriorating components known before a maintenance team ever comes in. This reduces the required time and therefore the cost of any maintenance.
As discussed beforehand, in the case of jet engines, run-to-failure maintenance is not desirable due to the hindrance it can cause in flight schedules and the high cost of the jet engine itself, not to mention the safety risk that flying with broken engines imposes. When comparing preventative maintenance and predictive maintenance, we found predictive maintenance to be more effective as it optimally minimizes the number of maintenance periods for an engine according to live data on engine degradation. In contrast, preventive maintenance is conducted off a fixed schedule, leaving engines already in good condition to undergo unnecessary time and maintenance. Consequently, researchers devote more time and effort to finding the best models to determine when to conduct maintenance. Here's our successful approach to creating a predictive maintenance model for an aircraft jet engine. Our model can predict the jet engine's RUL, also known as remaining useful time of life. RUL is a practical, industry-standard metric measured in cycles for a machine, and a cycle is a single use of the machine. For example, one jet engine cycle refers to a single flight. This failure rate data will come from a sensor that records the status of the component over time, and we worked with NASA's MAPSS, the Commercial Aircraft Engine Simulation Dataset, to get sensor readings for our model.
After the RUL of an engine has passed a certain threshold, and this threshold may vary for different airlines, an airline maintenance team will know when an engine needs to be either maintained or replaced. We decided to calculate this threshold by seeing when the failure rate found by using the RUL data as input, which is then multiplied by the cost of an engine failure, is equal to the cost of maintaining an engine that has not failed. Ergo, as the failure rate increases and the multiplied value exceeds the cost to maintain that engine economically, the airline should reschedule other aircraft to take the same route and gracefully maintain or replace the engine without harm to the airline's delicate flight schedule. In order to get data about engines, we defer to the MAPSS also known as the Commercial Modular Aero Propulsion System Simulation. This is NASA's simulation of many different types of jet engines, specifically turbofan engines. In different states, going through the data, we immediately noticed that some of the values were exactly the same throughout many different tests, only changing for a single data point over tens of thousands of time slices. We dropped all of these values simply because there would not be enough change in the data to create an accurate correlation of what these small deviations really mean to the model. The model may overfit these small changes if it did take it into account. Other data points like engine ID were also dropped because these would clearly not be consistent among engines from other companies and therefore could not be used. While we diligently looked for a company's data of real engines, no company would post data about their engines.
In order to calculate the RUL, which we can use to find when maintenance will be required, we use a long short-term memory model known as LSTM model. The model works best when there is not a single point of data, but a stream of data over a long period of time. This is perfect for our application as LSTMs are good at classifying certain states and making predictions about what state might come next. In our case, we give the model information about how the engine is running based on embedded sensors before asking the model to predict the RUL. The model has input gates, output gates, and forget gates. The input gates make a decision of whether a new piece of data from the current state will be stored and used by the model, while the forget gates decide whether an old piece of data will be thrown out of the current cell. From here, the output gates use logic and weights by looking at patterns in the training data to determine which factors are the most important and how to incorporate them. It then spits out an output from 0 to 1, which is then normalized for the true desired output.
Another way we prepare data for the model involved windows and shifts, which leads to little chance of an in and outlier. The window method gives the model a few slices of data at once. For example, we give the model 30 seconds of data with 1 data slice per second. Then we make a shift of 5 data slices showing 25 of the same seconds to the model and 5 new seconds of data. This allows for outliers in the data to be smoothed, thus making it less likely for pilot input or extraneous circumstances to trigger false flags. For each input, we calculate an RUL and average these estimated RULs to create a final RUL from the previous cycle. Compared to other models, the LSTM model is better because it solves for the vanishing gradient problem, where traditional RNN, recurring neural networks, will either ignore old data or weigh it as infinitely important, making it difficult to use simple RNNs in this application, thus making the LSTM the better choice. This is important as certain data points and flags created by centers can be benign on their own, however they may become dangerous when combined with other problems at some later point. Therefore, the LSTM's ability to properly weigh the importance of the past information with current data is integral to the success of this model.
We cannot simply look at an RUL and figure out when to conduct maintenance or replace an engine. To compute an estimate for the best time to perform maintenance, we need to be able to quantify the estimated damages if maintenance is not conducted and compare it to maintenance costs. We do this by taking the RUL estimate of the engine and then trying to find the percent chance of failure within the next cycle. We can multiply this chance of failure by the theoretical cost of an engine failure would give us an expected loss. This cost of an engine failure not only includes the actual cost of the engine, but the costs associated with the engine going down in the air. For example, if an engine fails during use, it's more likely for the engine to break significantly and require more maintenance as a whole. Not only that, when an engine fails at an unplanned time, that plane cannot simply go back into the air for its next planned flight, which means schedules must change, possibly causing delays, cancellations, and unplanned and expedited repairs. These unplanned maintenance cycles must be done quickly, and therefore are expensive for the manufacturer. This leads to a formula of expected loss from a single engine failure. Note, because regular engine failure has not caused a crash within the last 2 decades, it can be ignored from this formula. By multiplying the expected damages with the percent failure in the next cycle, we can find the expected loss of letting the engine fly one more cycle. By comparing this to the price of maintenance, we can simply say that the best time for maintenance is when the cost of letting the plane run one more time exceeds the cost of maintenance. It's important to note that the costs are not constant. For an airline, maintenance of an engine on an airplane may be more costly at some point in time rather than another, and the cost of delays may be more important at some point in time rather than others. For example, holiday season, which means the RUL threshold which an airline will replace an engine is not a constant but a function based on the current conditions. For example, if there is a shortage of labor for an external reason, it may be more beneficial to simply let the plane fly because the current cost of maintenance has increased, or repairing the cost may lead to a different delay. Therefore, it's cost effective to simply let the plane fly once more.
In this way, we get to our last variable that goes into cost of not maintaining an engine, reputational loss. To calculate the cost that airlines incur from loss of reputation due to engine failures based on past delays, we require sales data from these airlines. Unfortunately, none of it is accessible as a regular researcher due to the fact that these figures are often protected trade secrets. Therefore, it is our recommendation that airlines use their own values for the cost of reputational loss by taking the dip of sales after an engine has failed and using the trends to determine how much profit they have lost due to their reputation taking a hit.
So as we've discussed so far, jet engine maintenance is required to maximize the airplane's functionality and to minimize the likelihood of jet engine failure. Although frequent maintenance may prevent jet engine failure, it can become very expensive for airlines. Hence, our recommendations focus on striking a balance between over and under maintaining the jet engines. This helps to decrease maintenance costs and to minimize engine failure during flight. In our model, we examined our recommendations under the lens of insurance, behavioral changes, and modifying outcomes. However, we very quickly realized how difficult insurance for airline fleets would be. To give an example, we estimate that American Airlines fleet is valued at around $146 billion. Given how massive this fleet is, large airlines typically only carry passenger liability insurance. Further, the airline industry is not a oligopoly, and there would not be enough paying customers for insurance to cover their losses in the case of a payout. Yet our model's ability to analyze RUL and to use it to determine the likelihood of engine failure can certainly lead airlines to make behavioral changes. In other words, we can help them to decide whether or not to keep a jet engine running. Since our model can use RUL to find the likelihood of jet engine failure, engines can use this likelihood in combination with our expected value analysis to make more informed decisions. Nowadays, many airlines utilize a more modern approach to maintenance than pre-designed schedules. Predictive maintenance is becoming more mainstream and because more data is being inputted and recorded. That has been the largest shift in behavior towards jet engine maintenance. We expect airline companies to continue moving this direction for the maintenance of engines. Plus, as a better and more comprehensive data is collected on engine degradation, actuarial teams will be able to build even better models. We also believe that modifying the outcomes of engine failure can be crucial in limiting the risk that airlines face. The more common consequence of engine failure is the cost of replacing the engine, which, depending on the model of the airplane and the engine, is approximately $20 million. In order to determine this likelihood of failure, an airline would need to record lifetime sensor data on each engine and input this into our model for calculating the RUL. Then, our exponential regression should be used to determine the likelihood of engine failure. Although there might be minor administrative costs associated with this, these are negligible compared to the tens of millions of dollars required for jet engine replacement, which can be caused by physical damage to the engines.